Hello, class. Hopefully this finds you well. This is going to be how we conduct class for a while. Hopefully it works out well. If not, we can make some adjustments. So feel free to leave me feedback or shoot me an email if something's not working or if you're having issues or just have anything to say or questions or anything. Okay, so please feel free to contact me and I'll get back to you as soon as possible. So what we're going to do here is go through the PowerPoint the same that we've always done. Please have your note guide ready. If you don't have that, a notebook will do just fine. So take notes, and then we'll do some homework problems, and then hopefully it gives you enough information and knowledge to be comfortable to do the homework that I assign. I'll try to make the video short and often so that you can do a little bit of material and then maybe take a break, do some problems, and then do a little bit more. So try to make them about 15 minutes, but we'll see how long it takes to get through this material. I think today's might be a little longer just because we got a couple things to get through. What I want to get through today is I want to get through how to determine the pH of a mixture of acids and then how to determine the pH of polyprotic acids. So that's when you're done watching this video, we're hopefully comfortable with that. And then with a little more practice on doing our homework, we can do that. So follow along. Feel free to pause the video. I'm going to ask you to pause the video a few times just to work ahead, and then you can check your answers. The worksheet that we're going to be working off of today is 10.2. So we're going to be working on our note guide and then worksheet 10.2, and I'll assign a problem from 10.3 as well. So let's get started. And as you can see, I'll get better at this, but I'm somewhat new to this program. I'm not the greatest at making videos, so I'll get better, and this will become more smooth and hopefully better overall as the time goes on. But let's get started and see how this works. So I'm starting with how do I determine the pH of a mixture of acids? Now, anytime you have a mixture of acids, one is probably going to be stronger than the other unless you have the exact same acid. If you have two strong acids, like we will in the first example, I guess one might not necessarily be stronger than another, because if they're strong, what do you know? You should be thinking they dissociate completely. So if I mix two strong acids together, I can get the concentration by simply looking at the concentration of each of my acids. But if I have weak acids where the K really matters, okay, I can focus on who is the strongest first. Because typically the strongest acid is going to make the most impact, in my solution. So remember, K is products over reactants, okay? If I have a stronger acid, I have a bigger K. A bigger K means it favors the products more. Okay, so hopefully we're comfortable with that. Strong acids have a very large K. Sometimes you'll be given just a very large K, or sometimes you should just know it's a strong acid. And how do I know it's a strong acid? Remember, I have that list of those 8 strong acids on the half sheet, or also in my note guide. Okay, or you can just look them up. Remember the strong acids. We have to be comfortable with the strong acids in this unit. Okay, so what we need to do first is focus on a problem dealing with two strong acids. But again, if you're dealing with weak acids, look at the K. A big K means it's a stronger acid than a little k because it favors the products more. All right, so what if I mix acids together? If I mix acids together, my hydrogen ion concentration is changing. There's a new hydrogen ion concentration because I'm mixing things together. I could figure out the hydrogen ion concentration of just this, okay, by looking at this. I could figure out the hydrogen ion concentration of just this by looking at this. But when I mix them together, they're both going to change. Why? Because my volume's changing. Now, I should recognize that HCl is a strong acid. HNO3 is a strong acid. They're both strong acids. Okay. So how do I determine the pH of a mixture of two strong acids? Well, I need to first determine my hydrogen ion concentration. Okay? What is my hydrogen ion concentration of both of these strong acids? Well, I'm going to focus on one at a time. Because remember, my hydrogen ion concentration of this is no longer 1 molarity. It's changing. Why? Because I'm mixing it with 100 milliliters of a stronger acid. Okay? So I need to determine that new molarity. To determine a new molarity, I first go to moles. So I'm starting with a volume of my acid. I turn that to moles. So this is how many moles of H, or HCl, or Cl, I'm just focused on the H though, are in 50 milliliters of 1 molarity HCl. But what is my new concentration? My new concentration depends on my new volume. What is my new volume? Well, I'm mixing 50 milliliters with 100 milliliters. So what is my new volume? 150 milliliters. So what am I going to do? I'm going to divide this by 150 milliliters, or 0.15 liters. And that gives me my new concentration of H based on my new volume. Okay? Good. All right. Then I'm going to do the same thing for HNO3. And I'm going to determine my new concentration of H from HNO3 based on mixing them together. And again, both of these individual hydrogen ion concentrations should go down because I'm diluting them. Okay, I'm starting with 100 milliliters and I'm ending with 150 milliliters. So I determined the moles of H from my HNO3. Now to determine the new concentration of H from that HNO3, I divide by my new volume. My new volume is 150 milliliters, or 0.15 liters, and there is my new concentration of H from HNO3. Now how do I determine the pH? Well, remember the pH is the negative log of the hydrogen ion concentration. And what I have here is hydrogen from HCl. What I have here is hydrogen from HNO3. Well, how do I get the total hydrogen? Hopefully, you're ahead of me and just say add them together. If I add them together, there is my concentration of hydrogen from each. Okay. Now to determine my new pH from the mixture, I need to take the negative log of that. And when I take the negative log of that, I get my new pH, negative 0.362, which makes sense because I'm mixing two strong acids together. I'm going to have a very low pH. All right, so that's a mixture of two strong acids. What about weak acids? So here I have a mixture of two weak acids. How do I know they're weak acids? Because look at my K values. Here's my K value for HCN. Here's my K value for HNO2. They're both weak acids. Now, remember when I said if you want to determine the pH of a mixture that contains weak acids, focus on the stronger acid first. And that, I guess that always, applies. If you want to determine the pH of a mixture of a strong acid and a weak acid, you should really focus on the strong acid first. Always focus on who's ever strongest first. Okay, so I'm going to do that. Also in this question, it says calculate the CN ion, cyanide ion concentration. Okay, so I'm going to do two things. First, I'm going to focus on my hydrogen ion concentration based on my weak acid. And then I'm going to take that and apply it to, First, I'm going to determine the hydrogen ion concentration of my weak acid, but the stronger of my two weak acids. And then I'm going to apply that to my hydrogen ion concentration of the weaker of the two acids. Okay? So, to determine the hydrogen ion concentration of a weak acid, what do? This is what we learned on Friday, and if you were gone, hopefully you can catch up quickly. But if you want to determine the hydrogen ion concentration of a weak acid, you should think ice. It's an equilibrium problem. I'm determining the hydrogen ion concentration of a weak acid through ice because it's not shifting all the way to the right. It's reaching equilibrium. Okay, so I'm going to focus on HNO2 first. Why? Because it's the stronger of my two acids. Okay, So I'm going to start with the stronger acid first. I write my equilibrium expression for my weak acid. You could include H2O. It doesn't matter. You know, it's not going to matter anyway. Okay. You could say this is H3O or H+. It doesn't matter. Okay. All right. So anyway, here is the beginning of my ice table for my weak acid, HNO2. Now, hopefully, we can fill the rest in quickly, where I know over on the left is minus X, over on the right is plus X and plus X, and this is what I end up with. Now, how do I determine this right here? How do I determine this? Well, I need an equilibrium expression. And if I need an equilibrium expression and I'm determining X, I need a K value. Anytime you are determining this, you need a K value. Okay, or enough information to get you that K value, which you're going to need. If you need to determine X, you need a K value. Okay, so anyway, my K value for HNO2 is right here. It's given to me in the problem. You could look it up in a textbook. You could look it up online. I tried to do the best I can on these worksheets and give you the K values, and I apologize if you look on the answer key and you try to do a problem and you're like, but you didn't give me that K in the question. That's my fault, and I apologize for that, but I tried to do the best I can. And there's a couple corrections I'm going to go over in this slideshow that I noticed I didn't give K values where I should have. Because on the AP exam, you will be given K values, okay? In real life, you can look up K values on Google or in a textbook. Okay, so there's my K value of this weak acid, and there's my equilibrium expression. Products over reactants. Now, when I do this, I don't want to do the quadratic. So what I'm going to need to do, or what I can do, is I can cross this out. Okay, I can cross this out. Now, when I cross this out, I want to assume, or I should write, I'm assuming X is really small. Okay, so I write assume X is much smaller than 5. Okay, so I was saying X is much smaller than 5. Now you could prove it with the 5% rule once you solve for X, but an easier way is just write assume X is much smaller than 5. Okay, now after I write that, I can go ahead and solve for X, and there is my hydrogen ion concentration if I just had this weak acid. Now this is where we left off on Friday, because if I determine the pH of just this weak acid, I could just take the negative log of this right here and I'm done. But now we have a mixture. We're adding to this. So now I have a mixture, so now what do? Well, I've determined the hydrogen ion concentration from HNO2. Now I want to determine the hydrogen ion concentration from HCN. And remember, I'm going to add them together. Because it's a mixture, to get my total hydrogen ion concentration from HCN and HNO2, I simply just add them together. Okay? Now, how do I treat this problem? I treat it like a common ion problem. And maybe you remember this, maybe you don't. We did this in the equilibrium unit, where we dealt with KSP, where it already had some of an ion. But I reached equilibrium. So what ion do I have in my next equilibrium problem? Well, I already have some H. Okay, I'm going to take this H and I'm going to add it to the ice table for my next weak acid, this. Okay, that's what I'm going to do. Because I know the hydrogen ion concentration from HNO2, now I need to determine the hydrogen ion concentration from HCN. But remember, some hydrogen is coming from this stronger acid. Okay, it's a weak acid, but stronger of the two. So now I'm going to focus on HCN, but again, remember, my concentration of H3O plus is not 0. My concentration of H3O plus is 0.045. That's what I got in my last ice table. This is a common ion problem, just like the common ion problems we did in the equilibrium unit. So now I finish my ice table, and this is what I get. To determine X, I need K. So I'm given K in this problem. I was given it on the last slide. I'm sorry I didn't give it to you on this slide, but it is right here. This is the K value that is given to me, or I can look up, and now I can solve for X. But I'm going to cross these out. Remember, I want to cross those out because I don't want to do the quadratic. And when I cross those out, you can write assume, okay, assume that X is much smaller than the smaller of the two numbers. So I'm assuming X is much smaller than 0.045. 0.045. Okay, I'm assuming x is much smaller than this. Okay, so I'm assuming it. That's a very ugly less than sign. Here we can go and make it better. Okay, much smaller. Okay. All right, so now I'm solving for x, and that's x. So this is my cyanide concentration, and that is one of the two answers that it asked. One of the questions was, what is the cyanide concentration? There it is. And what is the pH? So the pH, remember, is dependent on the H3O plus concentration, okay, the hydrogen ion concentration. So to get the hydrogen ion concentration, I'm going to take 0.045 plus x. Hopefully you can see that 0.045 plus this number right here is 0.045. Why? Because that number is tiny. It's tiny. Remember, it didn't matter. Okay, so I can ignore it. So what I'm doing is I'm ignoring x, and it's definitely less than 5%. So my concentration of H3O or H plus is 0.045. To get the pH, I take the negative log of that, and there's my pH. So these are my two answers, okay, right here. This is the pH, and this is the, and this is the cyanide concentration, okay? Hopefully that makes sense. All right, so that's a mixture of a strong and a strong and a weak and a weak. Why don't we look at our homework next? We're going to look at 10.2, and we are going to look at a strong and a weak. Okay, so how do I do a strong and a weak? Well, remember, what do you focus on first? Hopefully you're saying the strong. I focus on the strong first. So the stronger of the two is that. So there's my concentration of H plus from HCl. Now I can take that and apply it to my weak acid. And I apologize, on your worksheet, I did not give you the Ka of this weak acid. That's what this is. So this would be given to you and should be given to you in the problem. I will go ahead and give it to you on part B as well in a later slide. Okay, so here is my Ka of the weak acid. All right, so now how do I determine the hydrogen ion concentration of my weak acid? Because I know the concentration of my strong acid. Well, you should say ice. Okay, ice. I ice to determine the concentration of a weak acid. All right, now, in this equilibrium problem, I already have some H. It's a common ion problem. So this concentration of H is my initial concentration right here. Okay, because this is supplying some hydrogen. It's not starting as 0, it's starting as 0.1. So then I'm going to reach equilibrium. I'm going to reach equilibrium like this. My concentration of HOCl is 0.1. My concentration of H is 0.1. I'm determining the concentration of H at equilibrium and OCl if I want. Okay. So anyway, I would take a second and pause the video if I were you and try to finish this problem, and then hit play, and we'll run through the rest. Okay. So I'm going to keep going. To do this problem, I'm going to finish this ice table. Hopefully we're comfortable with that. Next, I write my equilibrium expression using my Ka value. That is given to me in the problem. Again, I should have given that to you. Okay. All right, so now I'm going to plug them in. There we go. What can I ignore? What can I ignore? Okay. Hopefully, we can say I'm going to ignore this x and this x, cross them out, and I'm going to assume x is much, much smaller than 0.1. I could prove it using the 5% rule. I can just assume x is much smaller than 0.1. Now I'm solving for x. X is that. Now, for my hydrogen ion concentration, 0.1 plus this tiny number is 0.1. So to get the pH, I'm going to take the negative log of 0.1, which you should be able to do in your head. The negative log of 1 times 10 to the negative first is 1. Okay, so there's my pH, and there's my problem. You can do problem number 15b just like this, except I need to give you the Ka for that, which I will in just a second. Okay. Now, if I wanted to prove that 5% rule, once I solve x, I would take it and divide it by whatever number I'm subtracting it from. Okay, so to check assumptions, I take x, divide it by what number I'm subtracting it from, and make sure it's not less, making sure it's less than 5%, because then I can ignore it. So is 3.5 times 10 to the negative fifth less than 5%? Oh yeah, it's tremendously less than 5%, so it's definitely okay that I ignore x here. All right, so that's again why I can write this. X is much less than 0.10. That's why I can write that. Okay. All right. So on worksheet 10.2, part B, this is the Ka value of acetic acid. This is a strong acid. This is a weak acid, very similar to the problem we just did. But I apologize, I did not give you the Ka for acetic acid. So here it is. Write it down, and then you can do that problem. Okay, check your answer on my website. All right, we got one more topic to cover. That was mixtures. We're going to cover polyprotic acids. All right. Oh, sorry, I did forget. Percent dissociation is something that I forgot to talk about. It's kind of what we just did. Percent dissociation. What you're figuring out is you're figuring out how much acid dissociated from the initial. So what is your hydrogen ion concentration after divided by what was the concentration of the weak acid initially? And that is your percent dissociation. We're going to do a lot of problems involving this. I just wanted to introduce this key term now. And then we're going to come back to this, definitely this unit, and do some problems where maybe I give you the percent dissociation and you use that information to fill in your ICE table. So percent dissociation, if I determined in my ICE table the concentration of H of 1 molarity hydrofluoric acid was 2.7 times 10 to the negative second, my percent dissociation would be this divided by the initial concentration times 100. It would have been a 2.7% dissociation. Okay, so we're going to come back to that later on, but you might see that in some questions in the near future. So, all right, polyprotic acids, excuse me. Poly means more than one. So these are acids that lose more than one hydrogen. So anytime you see an acid that has H2, H3, okay, things like that, these dissociate one at a time. So if I look here, this acid becomes this, and then this acid becomes this. And they each have their own K values. So this is be called a diprotic acid, or a polyprotic acid, just is an umbrella for all of them. Okay, so using Hess's law, and this takes us back to earlier, if I wanted to determine the overall K, I would multiply the two. Okay, to determine the overall K when calculating the overall. But when calculating pH, remember you're going to focus on the stronger of those acids, because this is essentially a mixture of acids. This, it contains some of this, it contains some of this, and it would contain some CO3, okay? But it's a mixture, all right? So we're going to treat it a lot like those mixture problems. Each one of these have their own K values, just like each weak acid has its own K values, okay? So typically, the first dissociation, or the first equilibrium expression, has the biggest K. And they usually get much weaker after that, typically by a factor of 100 or more. Why? Because the conjugate base of the weak acid is a pretty good base. Remember, a weak acid, the conjugate base of that is a pretty good base, so it's not going to really want to donate another hydrogen. So it's going to have a much smaller K value. Okay, so we are going to look at this problem. Find the pH of 5 molarity H3PO4. And this has a lot going on because there's 3 H's there. There's 3 H's. So I'm going to lose, or I'm going to have at least 3 different K values. Okay, so I'm going to have a K value for here. I'm going to have a K value for here. And I'm going to have a K value for here. And those would be labeled Ka1, Ka2, and Ka3. So what we're trying to find is the concentration of each of these, the overall pH, and then the concentration of PO4 at the end. So we're going to break this down into really 3 steps, and we're going to do 3 ice tables. Like I said, this unit is going to be a lot of ice tables. Okay, so let's look at the first example, or the first ice table. So I have find the pH of 5 molarity H3PO4. So to find the pH of this weak acid, I do an ice table. Here's my ice table. My Ka1 would be given to me. So I'm setting up my ice table. Here's my Ka1. Okay, now what can I do? I can ignore that. And I can write, assume x is much smaller than 5. And that allows me to ignore that. And then I'm solving for x, okay, down here. So here's x. Here is my hydrogen ion concentration, which is also equal to my concentration of H2PO4. Okay, so I just did a normal ice table, just like I did on Friday, just like I'm doing today. I'm determining the concentration of H3O, which also equals my concentration of H2PO4. Now, I have H2PO4 here, which you should say, well, what is H2PO4? That's another acid. So what do I need to do to determine the dissociation of this? Well, I'm given another K value. So now I'm going to need to write a dissociation equation for this H2PO4 substance. Okay, so to do that, I move ahead. Oh, sorry. It seems like I forgot a couple things here, and that's what I'm going to be doing next. Okay, so anyway, like I said, to determine the pH of this solution, I can just focus on the strongest of the 3, which ends up being this H3PO4. So I determine the pH by taking the negative log of the hydrogen ion concentration, the negative log of 0.19. Okay. All right, so there's my concentration of H3PO4 at equilibrium. So that's one thing done. Now I'm going to determine my concentration of H2PO4, and I'm going to determine my new concentration of H3O+, which probably isn't going to change because this is a much weaker acid than this is. Okay. All right, so I'm going to focus on H2PO4, another ice table. So there's my next ice table for my next weak acid. So it's going to dissociate and make HPO4. Notice how it lost an H. So I'm doing another ice table for that. Here's my concentration of H2PO4 that I got in my last problem. My concentration of H3O+ is not 0 because I'm getting some from my first acid, my first dissociation equation. And now I'm doing an ice table, and I'm solving for x. Okay, looks like I'm a little out of order here. I apologize. Okay, so I'm just going to put everything up here and kind of walk you through it. All right, so here was my ice table right here. Okay, next, I plugged it into my equilibrium expression. This K value I would be given. And then I ignored these right here, and I wrote assume x is much smaller than 0.19. And then I solved for x. So now this is my HPO4 concentration. The H3O+ concentration hasn't changed, so that's why I determined the pH in the last problem, because 0.19 plus this little tiny number is still 0.19. So now I have a concentration of HPO4. I can also figure out my concentration of H2PO4 by taking 0.19 minus this, which ends up being 0.19. So I'm done with my concentration of H2PO4 as well. All right, last one, HPO4. So what is that concentration? Right here. That concentration is right here. So now I'm going to take that and plug it into my ice table. All of my other information I calculated from earlier ice tables. So now I have my Ka3 right there, and I am ignoring x. I'm writing assuming x is much smaller than the smaller number. Then I solve for x, tiny number. So this is my concentration of PO4. If I added that to my hydrogen ion concentration, it would be nothing. If I subtracted it from my HPO4 concentration, it would be nothing. So all this is really doing is calculating my concentration of PO4. The H3O+ is still 0.19. My pH is still 0.720. Okay, so there is a polyprotic acid calculation. Not going to see a lot of those on the AP exam, possible, but not very likely. I do assign one problem like that on worksheet 10.3. So that is today's lesson. Your assignment is to finish 10.2 and 10.3 number 1. I'll try to make the next video tonight, otherwise I'll do it in the morning for bases, and that will allow you to finish worksheet 10.3. So hopefully this was a good start. Please leave me any feedback that you want, and I will try to do my best to improve these videos to best serve you. And if you have any questions, feel free to email me, and we can take care of those. Okay?